Wanted to see what I have given you. I'm not sure that I put up part of what we'll cover today, but let me check. Yeah, if we get into 12, I think we only have the first three sections there, but that's probably all that we'll be doing. But maybe we'll get into the next one, but I'll be posting it as soon as possible. Okay, we're going to be looking at the block design in section 2 of chapter 12 to start with. We did a little bit of that last time, but I want to go over it again. There's still going to be one piece that will be missing. You know, as I went through the notes that I had developed. I'm going to go ahead and knit this. So randomized block design, just to review, this is in contrast to the one-way analysis of variance. Depending on how you replicate things, we can call a completely randomized design for the one-way analysis of variance. In other words, if you have a single treatment and you could divide individuals into, say, A groups, and then you randomize the treatments to the groups. So there's no bias in terms of what you measure on what group. So in that case, for example, if you had variety, you would have your response is a function of variety, where variety is a factor. And in that case, you would be comparing varieties to each other. You could do multiple comparisons or whatever. But suppose you have a lot of variation, because you're going to be planning these on, say, farms, and it might be that you plant all the varieties on the same farm, in which case you might control the variation okay. But if you have multiple farms, what you might do is plant each variety on each farm, but then do it multiple times. And so in that case, you would have a farm effect, but farm would be random, whereas presumably variety would be fixed. So that's a typical model, that you have a block, and what you're trying to do is to control the variation by removing the farm variability, because you're always comparing the varieties to each other within a farm, then you're pooling across farms. So you remove the farm variability, and your error term hopefully will be quite a bit smaller because of that. So we're going to assume there's no interaction between the farm and the variety. Now this is an assumption, and this may or may not hold. The problem is that the way this is formulated, you don't necessarily know whether there's an interaction or not, because that interaction will be confounded with the error term. In other words, you can't separate it from the error term. Now there are some efforts, there are some ways that you can, to a limited degree, try to pull out the interaction, a part of the interaction effect. In other words, the degrees of freedom will be A minus 1 times B minus 1, where A is the number of treatments and B is the number of farms, let's say. And so there are degrees of freedom you could pull out to try to estimate certain components of the interaction, but but in general, the interaction is confounded. So what you're hoping is that there's no reason to suspect an interaction between the treatment and the farm. Now, of course, that might not be the case. So again, that's an assumption we have to be careful about. So that's our basic model. It will be mu plus alpha sub I plus beta sub j plus the error term. And the alpha will be the treatment effect. It can be either fixed or random. So if it's fixed by the construction of the alphas, we will be saying that the sum of the alpha sub I is equal to 0, or that the alpha sub i's are independently normal distributed with mean of 0 and variance sigma squared sub I, if it's a random effect. Beta is going to be a random effect. It's going to be independently normal, mean 0, variance sigma squared sub b. And then the error term will be, again, independently normal, means mean of 0, variance sigma squared. So you have two variance components here. You might have three. You have at least sigma squared and sigma squared sub b, and then you might have sigma squared sub a if, in fact, a is a random effect. So let me go back and take a look at an example. Suppose that, by the way, what I'm doing here is I'm saving the current state of the options. The options are sort of global parameters for R, so I'm saving the current state of that. When I say I'm going to set, these are global options, I'm going to set the contrast. Notice I have two sets of contrast, and the first set corresponds to factors. So like if I have the treatment effect, it would use the sum contrast, the sum of the alpha sub i's equals 0. That second one would be if I have an ordered factor. So if I have a factor that has order to it, like small, medium, and large, then you can have in R both factors and ordered factors. And so it's by default going to use the sum contrast. And by doing this, it makes it global. And so in other words, I'm setting the options to be global, although at the end of this, I set it back to be whatever it was before, which the default one is the alpha sub I equals 1. Alpha sub 1 equals 0. So at any rate, I'm going to read it. What we're going to do is we're going to look at a psych experiment in which you have 4 subjects, and those subjects are going to be a block, because each of those subjects are going to get administered 3 treatments. So every subject gets 3 treatments. So a subject becomes a block. Because in a block design, we're going to sum each block gets each treatment exactly once. And then what you're going to measure is the length of time to complete the task. So there's a data set called task.text. Let me first of all do the options, and then we're going to read in task. So we could look at task, and so it's a pretty small experiment, but notice it's subject, treatment, and time. And then let's attach task, so I can just use the names directly. And then I'm going to make, notice that both subject and treatment are at 1, 2, 3, or 1, 2, 3, 4, and 1, 2, 3, respectively. R is going to think they're continuous variables, so I need to convert each one of those to a factor. So I'm going to say factor of subject is subject and treatment is factor of treatment. And then I'm going to fit a model. Now the basic print for this object doesn't tell you that much. The basic print just tells you the formula, and these are the estimates of the coefficients. And notice there are 4 subjects, but because the sum of the alpha sub equals 0, alpha 4 is not displayed, which would be subject 3. And if you wanted to compute it, it's minus the subject 1 minus the subject 2 minus, it's the addition of the minuses of each of those. And likewise, there are 3 treatments, so we have alpha 1 and alpha 2, these are actually alpha hat 1 and alpha hat 2. They're the estimates of the alphas. And to get alpha hat 3, it's the sum of the negatives of those. Okay, so in order to get a nicer print, or I can just do an analysis of variance table. So if I do an analysis of variance table, then you can see that for subject and treatment, notice that the p-values are both very significant. Now you might ask the question, the function called AOV, I'm using ANOVA, that's right, which there's an AOV function, which is just a wrapper for LM. The ANOVA basically does the same thing. It's operating on the LM object to create analysis of variance table. Now, the problem is LM will just use the residual as the error term for everything. And so you might ask, okay, in order to get those two F values, I divided each of the mean squares. I divided each of these mean squares by this residual variation, 0.0756. Turns out that's correct. If you look at the book, and I'll add this to the notes, but if you look at the book, that both of the, since we don't have an interaction, and you'll see later when we get to two-way analysis of variance, this makes a big difference. But since we have no interaction, then if you look at the expected sum of the squares, it's assuming that treatment is fixed, it'll be just sigma squared plus some expression in the alpha sub i's, and the variance is sigma squared. So you're going to test treatment by the residual. Likewise, subject is sigma squared plus some function of sigma squared some beta for the subject effect. And so again, you test it by the error term. The book gives the exact formulas, and I'll add that to the notes. But the point is that we use the residuals to test both of these in this case. So they're both highly significant, and that indicates that there is a lot of farm-to-farm variability. And, you know, in fact, if you could get an estimate of the variability due to farms. And, you know, based on these mean squares, we could get an estimate. And if you did this, you would see that most of the variation, the variability due to farms is much greater than the variability due to residuals. And so there's definitely a large farm effect. If you would not have, let me tell you what would have happened had you not broken out the farm effect. All that sum of squares for the, well, I'm sorry, I'm talking about subjects here, no longer about farms and varieties. The subject effect is pretty significant. In other words, the subject variability is very, very high. What would have happened had I just fit treatment and it ignored the subject? Then this whole sum of squares right here, this 32, would have dropped down into the sum of squares for the residual. So that would have been about 33 point something, but the degrees of freedom would now be 11. Okay, you understand what I'm saying? If I wouldn't have fit it, that sum of squares due to subject would be down. It would be pulled with this along with the degrees of freedom. So you would have had a residual of 11, and then the sum of those two, which would be 33 point something. So you would have divided 33 point something by 11, which would be about 3. So your residual, your mean square would be about 3, a little over 3, and it would still be significant because if you divide 22 by a little over 3, it's about 7 something. So you'd still be significant with your F-test, but not 291. You'd be way less than that. So I don't know exactly. I think later on in the notes I maybe do it that way. So at any rate, it was worthwhile to block. Now sometimes you can't give a treatment to each subject. In other words, if it's a medical procedure and you have 3 treatments, you're going to pick one treatment to give each patient. You're not going to give all 3 treatments to each patient. So sometimes you can't block that way. And in that case, you would really have a two-way analysis of variance where you have subject treatment, subject by treatment, which we'll be talking about the two-way either later today or next Monday. So in that case, you would not be able to you would not be able to block if you could only apply one treatment to each patient, or if it's a patient, let's say. So, so at any rate, if you want to actually see the results in terms of the model parameters, these are the model parameters, and you saw that before when you got the basic output from the basic model fit. Those are the model parameters. And I had intended, I'm going to hold off on this next section. I'm going to come back to this a little bit because it gets into a topic that's fairly important, but I need the way this covariance matrix is defined. I'm going to need to look at that a little bit because it tends to differ from what JMP has. So I'm going to hold off. I'm going to hold off on this. What I was trying to do here was to compute the model, what I call the model means. And there's a little bit of confusion about what model means are versus the regular sample means. So if you wanted, how do you think that you would get the means? You can think of this as a matrix where you have subjects as rows and columns you would have treatments. So that would be a 4x3 matrix. So how do you think, and you have 12 values for that matrix. So how do you think you would get the means? Well, you would think that logically I would just, for the first column I would average over subjects. For the second column I would average over subjects. And so you would get an estimate of the mean for the treatment 1, treatment 2, treatment 3 that way. So those are actually, that's not actually necessarily correct. And the reason is that, in this case it would be, but it's not necessarily correct. Let's suppose you have a table like that where you have subjects and you have treatments, and in each cell you may have different numbers of observations. Then just averaging is not the correct thing to do. So there's a difference between what we call a model mean and the sample means. In the case where the data is balanced, meaning that the number of combinations of, in this case, treatments and subjects is the same, and in this case it's always one. There's one subject with each treatment. That's what's called a balanced design. If as long as a balanced design, then the model means are the sample means. But in general, that's not true. The model means are also called the least squares means. I had a student in my next class come up to me and say, because I had asked him to do the least squares means, what are the least squares means? The least squares means are the model means. They're not necessary. You know, if it's a balanced design, then the sample means and least squares means are the same, but if you have an unbalanced design, then that's not the case. So what I was doing here was trying to show you how to compute the model means. And what I will do is, what I am going to do is if you look at task for a moment, I'm going to combine task with the fitted values. So let's take task and let me execute that. And let's print out task. And so what does this do? The first three columns is the original data set. What do you think that last column set is? Well, task fit, the fitted values are the y-hats. There are estimates of the actual values, the times. So notice that 4.7 is what we measured, but the model estimates it as 4.675. The time for the second subject, which is, it's the first subject, the second treatment, is 9.4, and so you notice it's 9.325. Notice that's quite close. And if you look down through them, most of those are very, very close. Those are my y, what we call y hats. And the way you get y hat, how do you think you would get the 4.675? Well, that will be mu hat plus alpha hat 1 plus beta hat 1. Remember that if I have test fit dollar sign, I think they call it. So if I would, subject 1, that's alpha hat 1. Subject 2 is alpha, I'm sorry, that's beta. Subject 1 is beta hat 1. Subject 2 is beta hat 2, beta hat 3, and then that's alpha hat 1, alpha hat 2. And then that intercept is mu hat. So the point I'm making is if you add 4.6 to 2.2, which is about, that's 6.8, right? And then you subtract 2.125, then you get the 4.675. Do you see that? You understand what I'm saying? That's this 4.675. If you take this and add it to this and subtract this, you get this. So how would you get the second one? You would take mu. Notice the treatment is 2. The subject is still 1. So you take this plus this minus this. Plus this, I mean. And so you get to 9.375 and so forth. So those are the way we get the hats. And those, in fact, are the model means. And then the question would, I mean, those are the estimated values. And the way that we could get the model means for the first treatment is to add this plus, for the first treatment again, this, well, I had the wrong one, this one, plus this one, plus this one, and add them up and divide by 4. Now in this case, that will equal taking this and adding it to this and adding it to this and adding it to this and dividing by 4. And that is because of the balance. That will not be true necessarily for an unbalanced design. I've said that an unbalanced design, if n sub ij in that table, in this case it's a 4 by 3 table, if n sub ij is the number of observation in the ith row and jth column, if those are all equal, it's balanced, but it's also true it's balanced if they're proportional by row or column. So balance doesn't necessarily mean just equal. But if the n sub ij's are different, then we have what's called an unbalanced design. And this is where things get a little more complicated. This book tends to focus on equal sample sizes for each cell. And if you're computing things by hand, then that's a convenient assumption. The problem is real data is not always like that. And so using a computer, that's not so much of a problem. I will come back to this topic a little bit. I need to fill in a little bit here, you know, in terms of, I actually, someplace I thought, yeah, there's something called a model matrix, and that's actually what's called the model matrix. And the model matrix is what is usually used internally by R to fix it. So you might ask, what is that? Well, those are the 12 observations, and the first row, notice if I multiply the first row times the mu alpha 1, I'm sorry, this would actually be beta 1, beta 2, beta 3, and So if I multiply the first row, that will be mu plus beta 1 plus alpha 1. So if I wanted y sub ij, and let's suppose I want y sub 1, 1, which is the first treated with the first subject, it will be mu plus beta 1 plus alpha 1 plus epsilon 1, 1. That would be yij, or in this case y11. And then the second one would be the same, except that I would have a plus alpha 2. And the third one, I would have a minus alpha 1 minus alpha 2. And so the model matrix is constructed from, in other words, this first column right here, subject, expands out to these three columns. These are called dummy variables. In other words, we don't fit 1, 2, 3. If we did, it would be like a regression. It would treat 1, 2, and 3 as numeric. We have to define categories, and the way we define categories is by dummy variables. So if I just look at subject, a 1, 0, 0 means the first group, or the first subject. A 0, 1, 0 means the second subject. A 0, 0, 1 means the third subject. A minus 1, minus 1, minus 1 means the fourth subject. A 1, 0 means the first treatment. A 0, 1 means the second. A minus 1, minus 1 means the third treatment. So I'm using these variables, but internally we construct x, and then x, the model is really x times the parameters, y is equal to x times the parameters plus this error term, and then it actually solves a system of equations based on that x, not the original matrix, because we can't treat treatment and subject as numbers. They just represent categories. So I'm not going to get into that into a tremendous amount of detail, but I may fill in the gaps a little bit more. But the model matrix, and you simply use the function on the fitted value, you say model.matrix, and that that gives us the information. But by the way, there's also something called model.frame. And the model.frame of task fit. Well, actually, I have to then convert it to a model matrix. But what this does is it simply puts the time first and then puts the two factors. This always puts the response variable first. So when it's fitting, internally the way the R works is it'll actually call a model.frame and then a model.matrix on it for the matrix part. So at any rate, that's an internal thing to R. Now, there's, going back to the notes a minute, and I'll follow up on that a little bit more. Usually, you're not particularly interested in those alphas and betas unless you kind of want to know the nuts and bolts of how you get what are called least squares means. And I have the least squares means and the standard errors for them, but there's actually, I believe there's an error here, so I have to recompute the standard errors. And I didn't have time to get that finished before I came. But here are the, here's another way that I can compute. I can compute the means for the three treatment groups. I can simply t-apply the fourth column of task, which, again, if I look at task, when did I do this? It's this. It's the fitted values of the fourth column. And so I can simply compute the what are called the least squares means or the model means by using, now I've lost it, by using by mapping the mean over the different treatments in the fourth column of tasks, which are the y hats, and these give me the model means. Okay, I've already shown you this model matrix. So this does the same thing, except it makes it into a matrix.
Now what I'm doing there is I'm taking, when I said with the means, I made them into a matrix, and therefore I'm taking the differences. Let me go back a minute. And if I compute those means, and then the outer product takes each mean with each other mean. So it actually creates, in this case, a 3 by 3 matrix. And I'm saying that I want a minus sign as the operator, so it's taking the differences of all possible means. So let me do that, and I'll show you what this does. The outer product is, if I take two vectors and I multiply each element of each vector and add them together, that's called the inner product. The outer product sort of the reverse. It multiplies each corresponding element, but it makes a matrix. So if I have a 3 by 3, it will make, if I have 3 in one vector and 3 in the other, it will make a 3 by 3 matrix of the multiplication of each element of each other. So the first position of the first one will give the 1, 1 position, and so forth. But I'm taking differences. So this says the operator I'm going to use. So if I do this, these are actually the mean differences. And so if I wanted to do Fisher's LSD, I would look at those mean differences and I would compare them to the appropriate t times the standard error, the difference. And if I look at the output, for Fisher's LSD, then I have that the difference is compared to the t-value. But what do you use for the error term? Well, you're going to use the MSE, the error mean square. And since the sample sizes are the same, it will be 2 times the error mean square over b, because I'm averaging over the b subjects. B is 4. I'm averaging over the 4 subjects. So in this case, I simply have t times the square root of 2 times the mean square over b, and that's 0.476. And then if I look at the standard error itself, it's 0.1947. And so I compare each of those differences. I actually compare them to this 0.476. So I'm asking which ones of these are bigger, and it appears that all 3 of them are bigger, because I'm taking the absolute value. So that means that all treatments differ from treatment 1 differs from treatment 2, treatment 1 differs from treatment 3, treatment 2 differs from treatment 3. They're all significantly different. So what I'm doing here is pairwise comparisons. But the problem is, remember that pairwise.t.test? By default, that only works on the one-way analysis of variance. So we have to do, there are ways you can make that work for the two-way. But by default, pairwise.t.test only works on the one-way analysis of variance. So if we have a two-way here, we have no interaction, but we have 2 factors. So by default, we can't use pairwise.t.test to get the pairwise differences. Now, again, you can kind of you can coerce it to happen. If I have a 4 by 3 as a two-way, in other words, I have 4 subjects, 3 treatments, I could coerce that into a one-way that has 12 levels. Does that make sense to you? Now, the problem with doing that is that it's going to say, well, if I fit a one-way with 12 levels, I would have 0 degrees of freedom for error, because I would use all my degrees of freedom. And I would have, for treatment, I would have 11 degrees of freedom, right? And for the correction factors for the mean, I have 1. And there are only 12 observations, so there are none left for the residual. There's no replication. So I couldn't do that, really. So in other words, we kind of had to do this by hand. Now, this is kind of one place that JMP has some advantage, although I'm going to give you some details on how we might be able to do this in a little more automated way. Because there's another function called ANOVA, A-N-O-V-A, with a capital A, which is not the same as the function ANOVA with a small a we're using here. Remember, R is case sensitive. There's a package called CAR, C-A-R. And within that package, there's a function called ANOVA with a capital A. And what that lets you do is mimic the way SAS does stuff. And I'm going to be introducing that at some point, but not today. So what I'd like to do is I'm going to go in to get the data set. Oh, I'm already in. And so here's the, I've already got it as a jump data set. In fact, I've already run it, so let me kill this. That's the data set in jump. And you could import the text file and get a jump file quite easily. So I have subject, treatment, and then these are the times. So how would you fit this in jump? If you were doing it in jump, you'd simply say fit model. And then time will be Y, so I'll click on it. And then subject, I'm going to add it, and I'm going to add treatments. So if you can think of it this way, time is like on the left-hand side, and then in R you have a tilde, and then you have subject plus treatment. So down here we don't have a plus sign, we just have the terms, and that's an implied plus in the way R's notation is. But what I'd like to do one more thing. I would like to say, well, subject is a random effect, right? So I'm going to go down and see where it says attributes so I can make it a random effect. So in jump, I say the subject is a random effect in treatment, and now, again, the method of estimating the variance components, I can do either of these. I'm going to go ahead and do the traditional, which is the way the book does things. And I'm going to run this, and when I do, I get, now notice, in their analysis of variance, they have treatment, subject, and here's the 2 and 3 degrees of freedom. And notice that that 291, remember that was the F value? And I hope that it was 144. So those are the treatments. Where was our output? Yeah, 144 point. Yeah, 145. It's rounding off. 144.5. Yeah, R is rounding off. But so in other words, the two F ratios are the same. And notice the p-values in jump. They don't give anything below 1 in 10,000. So it's saying the p-value is less than 1 in 10,000 for each of those. So it's highly significant. And by default, it prints out the residuals from the model. You can sort of see whether the residuals look well behaved. We could do that too, of course. But it also gives, these are the coefficients for the expected mean squares. And this simply says, since we only have a treatment here and a subject here, this says we're going to use the regular error term. And then here are the variance components. Remember the error term for the residual is 0.075, and that's the variance component for the subject variability. And you can see of the total variation of the two variance components that almost 98% is due to the subject variability, and with, the residual here is only 2%. And so you can see that there's tremendous subject-to-subject variability. Those are the variance component estimates, using the traditional method, which is what's done in the book. The RIML, the other method, RIML, is it's a way to avoid negative variance component estimates. Remember I said that there's nothing to stop this from having negative estimates using the traditional method, but the RIML will make it not be negative. So what we did in the traditional, we said, okay, if it's negative, I'm just going to set it equal to 0. So RIML has a little more sophisticated method of doing that. REML stands for, RE stands for restricted, and ML for maximum likelihood. Maximum likelihood is the main way, or is it principal way we estimate parameters, and it's the way we're estimating the parameters in our model here. So we're using a restricted method of estimation. Now you notice that the treatment effects, here are the treatment mean squares. This computes the standard errors. Now why does it give a least square mean and a mean? Why do you notice they're the same? But they wouldn't give it if that were always the case, would it? They wouldn't give a column that says mean and another column that says least squares mean if they were always equal. The least squares mean are a model mean, and again, if you have an unbalanced design, they're probably not going to be equal. Now the means we make inferences are not that last column. They are the model. We make inferences based on the parameters, and the parameters are used to compute the least squares mean. So we make inferences based on the least squares mean, not the sample means. It was very misleading if you have an unbalanced design to use the sample means. So again, we have standard errors, and I could go in and get a least squares means plot. Let's see. Okay, here's students T. Okay. Now what students T does is it computes these differences, which we already did, and then it computes the standard error of the difference, 0.1947, and then it gives confidence intervals, and then you're asking, does the confidence interval include 0? And if it does, it's not significant. If it doesn't, it is significant. So you can see that by the red, red means it's significant. So they're all significant. And also that bottom thing, there's no overlapping letters, and that also says they're significant. Now notice this 0.1947. If we go back and look at what we're doing, there's a where is it? Someplace. Oh yeah. If I do I'm just going to fit the model again, and I'm going to do something called model tables. And when I do a model table, that gives the least squares means, and it gives the standard errors for the differences of the mean, the 0.1947. Remember, that's exactly, if you look at that 0.19, so what this is, these are the treatment means, and then it gives the standard errors for the difference of the treatment means, which is what you need to compute whether or not Fisher's LSD is significant or not. But that is the same as this value, the 0.19747. That's, again, the standard error of the difference. Notice up here, the second position, it says it's a standard error of the difference. And then these two are the lower and upper confidence level. Now, so you might think that everything is okay with respect to the way R does things, but it isn't. And the reason it's not is if it's unbalanced, that standard error of the difference is not going to be correct the way R does it. Or not necessarily. I need to check that out on an unbalanced design, but well, it may be okay. It may be okay, and I need to check this if the error term is always the residual. But if the error term is not the residual, then it's definitely not going to be okay. And you'll see why this is a problem for R a little bit later. At any rate, I did want to just point out one more thing. Suppose we had sort of ignored, let's go back here. Suppose we simply, I'm going to call this task fit 2. Suppose we simply fit this model where we fit treatment and we ignore the subject. So I'm treating it as a one-way and I ignore the subject. And so now let's do an ANOVA of the fit. So I'll run this. Now notice, remember that 33 I talked about a while back? Notice that the sum of squares is now 33 for the residual and with 9 degrees of freedom, and the mean square is 3.7, so the F value is about 6. And notice it is significant, but it's barely significant. The problem is we have a lot of subject-to-subject variability, and if we threw that into the error term, then if it would have been a little bit worse, it would have made it non-significant. In other words, by doing a block design, we pulled out the noise of the subjects because we did comparisons within subjects. And so we get in a highly significant. Here it's still significant, but at that 0.02 level. Okay. So I think I'm going to stop here. I'm going to come back to this a little bit. The point I want to make about the block design is that it can be very efficient because it can pull out the variation due to the blocking factor, and it gives you a cleaner estimate of the error term. So that's part of what we call experimental design, and a block design is a key design. A lot of times in a medical situation, it may be called matching. I match subjects according to some criteria so that they have a similar age or whatever. And so again, I'm doing that in order to control variation. So in biostatistics or epidemiology, within the medical field, you don't usually block in the traditional sense the way we do, but it's equivalent to doing that. Again, you're trying to control variation. Okay, I'm not going to save that. I'm now going to talk briefly about controlling two sources of variability, but I'm not going to spend a lot of time on this. It's called the Latin square design. Let me change the working directory, and I'm going to knit this. The Latin square design is an attempt to control two sources of variability. So typically what you have is two treatments, and you have two blocking factors in one treatment. And this came about in agricultural experiments. When, and I'll show you where it came about in agricultural experiments. Suppose you have a plot of land, and let's suppose that it sort of slopes in two directions, and you're concerned about water drainage. You know, it's going to be drier at the top than it is the bottom, but the water's sort of going down at an angle. If it's sloped at an angle, then the water is cutting across this block. And so what you might do is divide the block into columns and rows. So you have like 4 columns and 4 rows that cut across each other. So you have 16 cells. It looks like a matrix. And then you have a treatment. Let's say you have, and this is why it's kind of hard, because everything has to equal. If I have 4 rows, 4 columns, I need to have 4 levels of the treatment. So suppose you have 4 varieties of corn, let's say. Well, maybe that's not a good choice. And so what I'm going to do is I'm going to randomly assign the 4 varieties of corn such that each variety appears exactly once in each row and each column. Okay. Now there's a lot of ways of doing that, and as the size goes up, if you have 10 rows and 10 columns and 10 treatments, then there are a lot of ways to doing that. But that's what we're going to do. And so what happens is we're going to remove the bias, because if we randomized it, we don't want all of variety 1 to be on the left and all of variety 4 to be on the right. Well, we don't want all of variety 1 to be in the upper left corner and all of variety 4 to be in the lower left corner. If it's drier in the upper left corner and wetter in the lower left corner, that would be bias. So what you're trying to do is control the variation, and so you're trying to spread out this variation among the treatments so that we control for it and we don't have bias. So that's the nature of it. And so we have a design like mu plus alpha sub I plus beta sub j for gamma sub k plus epsilon I j k. And what this means is y sub I j k is the ith treatment in the jth first, let's say, the row, and kth in the column. You can think of it that way. I called it the first extraneous factor and the second extraneous factor. Now the restriction is, again, that the number of rows, number of columns, and number of treatments all have to be the same. That's part of the reason I'm not going to spend a lot of time on this, because in agricultural field trials, you can probably say, okay, I want to pick the four. I'm going to have 4 rows, 4 columns, and I can pick the 4 varieties that I think are most important to compare. So in agriculture, you can sometimes make this work. And there's a lot of reason why you might want to do it in that setting. But if you get outside of agriculture, it becomes difficult to make it work. Okay, if the alpha sub I represents the treatment effect, and the beta and the gamma represent the extraneous variation effects, then I'm going to assume that the alpha sub I is either going to be fixed or random again. It's going to be the sum alpha sub 0, or just going to be the variance component due to sigma squared sub A. And the beta sub j and gamma sub k, again, are going to be variance components. They're going to be random effects of variance components. And the epsilon is going to be the error term. Again, we're assuming there are no interactions. And so that's another issue with this type of design. If there really are interactions, then we have confounding, because all of those interactions end up in that error term. Now, the good news is it tends to blow up the error term. So if we have significance, if we do have significance, then we're pretty sure we do, because any interactions go down to the error term. So that blows up what the error term should be. So if I'm dividing my mean square for my treatment divided by the error term, if it's significant, we're okay, because I've added stuff to the error term. But if it's not significant, you might say this: is it really not significant, or is it because I have confounding? I have these interactions down in the error term. And if I could break them out, then maybe I really have a significant treatment effect. And so, again, this just gives the computing formulas if you were doing it by hand. I'm looking at the total variation here, the y sub ijk minus the grand mean. This is looking at yi dot dot for the ith treatment minus the grand mean, and that's squaring them up. And this is the jth beta effect, the mean for that, and subtracting the grand mean, and the kth gamma effect from the grand mean, squaring them up. So again, if you're going to compute it by hand, this is where you're going to do it. And this is how we compute the degrees of freedom. They're all a minus 1, except for the residual, which is a minus 1 times a minus 2. And you can see that those 4 degrees of freedom will add up. Those add up to a squared minus 1 if you add them up. In other words, if it's 4 by 4, I'm going to have 3 degrees of freedom, 3 degrees of freedom, 3 degrees of freedom, and then I'm going to have 3 times 2, or 8. And so, is that right? If I had 4 by 4, 3, that's 9. And then I have 3 times 2 is 6. And so that would be 15, and then 1 more degree of freedom for the mean, which would give you 16 total observations. Notice that everything here, again, is divided by, all the f-tests are based upon the residual here. That's going to dramatically change when we get to the next section on next Monday. We no longer just use the error term. And so in this case, we can just use the residual to test all these effects. So if I look at, if I have an order, we have 3 subjects with 3 orders and 3 devices. So in this case, if you had 3 devices and you were doing audio, you could change the order of which you record the observation, which device first, which device second, and so forth. So you could have 3 orders and 3 subjects in this case. So I'm going to read this. This is actually a non-agriculture example, but these are relatively rare, although you can design it, to be this way. So let's take a look at this. So I'm going to read in the audio file, and let's go ahead and look at this file. Now notice there are 9 observations here. So the order, we have subject and order and device. So we have, we're interested in the device. In this case, that's the treatment effect we're interested in, is device. but I want to remove the bias. It might be because of the order in which I listen to things. So each subject, each subject 1, notice that, if I look at this, there are only 3 subjects. So each subject is going to do it each way, but they're going to, the first subject does the first, then the second and the third. The second subject does the first. Well, that's the way it is, but let's see. Well, that's not an optimal design. It works, but ordinarily you want to randomize those. Ordinarily you want to mix it up. Okay, I'm going to attach this file, and whoops, I didn't mean to do that, but okay. I meant to hit the run, and then I'm going to make subject and order as a factor, although I think it becomes a factor anyway for e.table, and then device I'm going to make into a factor, and then actually, what this is actually doing is mixing it up. Notice that the first one is in the diagonal positions. The second is in the second, in the 1, 2, 2, 3, and 3, 1 positions. And the third one is in the 1, 3, the 2, 1, and the 3, 2 positions. So this mixes it up. Now there are there are ways that you can do this using the computer that you randomize. That picks a particular order. That picks a particular design. It's not just the 1, 2, 3, 1, 2, in the order that would not be correct. And then if I actually now plot, let's say, the score by device, I can see there appears to be a difference. So what I'm going to do is I'm going to fit the model where I have score, tilde, subject, order, and device. And then I'll do an ANOVA. And what I'm interested in primarily is the device, and you can see that it's pretty significant. Now, had I not done this, had I only had devices, then the degrees of freedom for these two would have gone down into the residual. So it would have blown up this residual sum of squares. The degrees of freedom would have become 6 instead of 2. And if I would have added these two sums of squares down here, that's what we would have done had we ignored the 2 sources of variability. So basically, I'm not going to do very much on the block design. As I said, I'll probably add. I don't think I had the. I don't have the expected mean squares. I should probably add those. They're in the book. You can take a look at the expected mean squares. But in this case, they're very easy. Everything is tested by that residual term. Okay. So what I've done here is I've looked at 2 designs. The nesting is a type of design, but it's really a subsampling more than it is controlling variation. So in terms of controlling variation, the block design and the Latin square design are really the 2 that we've talked about. I want to just introduce today, I'm going to come back particularly to the block design and show you a few things more. But the main way I'm going to show you this stuff in terms of the model matrix is based upon, and I haven't given you this yet, this is section 4, And section 4, let me go ahead and knit this. Section 4 deals with what's called the a by b factorial. Now, that looks like a block design. You have y sub I ijk is equal to mu plus alpha sub I sub plus beta sub j. But notice there's another term, the alpha beta ij, which is called the interaction term. And graphically, I can show you what the interaction looks like. I think I may have some graphs at the very end of this. Here's an interaction plot. Here we have this example. Let's see, where's the example? Suppose you have three methods. We have 4 fields of whirl, and we have 3 methods of extraction. And I guess we're measuring output. And what you want to know is perhaps, is there an interaction between the method of extraction and the field of whirl? So just to show you, if you do the analysis of variance, the reason I'm sort of quickly going through this, I'm just trying to give you an idea today because we only have a few minutes left. But this is what we're going to cover next time in a lot more depth. And we might get into the 3-way design. If you notice, the method and field are both significant. The method is highly significant. In other words, the p-value is very, very small. And field is 0.027. It's significant, but not highly significant. The interaction, however, is also significant. Now, what do I mean by interaction? The best way I can explain it is to look at this particular graph. Down here, I have methods of extraction, and up here, I have the 4 fields. Now, notice that 3 of those 4 fields make sort of a V. If the 4th one, and the 4th one is what? Is that field 2? I think it's field 2. If the 4th one would have made a similar V, there would have been no interaction. The reason there's an interaction is because for the second field, the carbon dioxide method on the second field gives you a much lower yield. And because of that, you get an interaction. Other than that, they pretty much follow, there are slight variations there, but they're basically following the same pattern. So I can look at it that way, but I could also look at it in the other way. Here I have the field down here, and the method are the lines. And then the yield, which is the mean number of barrels. Again, this bottom one and this top one more or less follow the same method, but the one for carbon dioxide, which is the middle one, does not. Well, not as much. Actually, it's this one is the one that's very different, because instead of going up and then down, it goes down and then down. So do you sort of get the idea that an interaction is saying it's not just additive. If it were just additive, I would always go from here to here would be about the same. You know, going from here to here, these differences would sort of be additive. This effect due to changing a method would sort of be constant across levels of the other factor. But that's not the case. You can see that they also come together in a point. This particular method here drops much more quickly than this method. So, in other words, the solid line, is pressure steam, drops more quickly going to field 4. So, so we have an interaction. But that's called an interaction plot. And if you've got something like that, then that's an indication that there's a problem. Now, we could have done an interaction plot on our block design to see if there's a block, but the problem is each point only has one observation. In other words, an interaction plot with the block design, you would have done subjects versus treatment. And you could have gotten the interaction plot, but each point would have been just averaged over 1. Whereas in this one, each of those points What do I mean by a point? Well, that's a point, that's a point, that's a point, and so forth. And this says the mean of number of barrels. Well, if you actually look at the data, you're averaging over n, and in this case, did I tell you what n is? I didn't. But if you would actually, we'll print out the oil next time, and you can see that n is not 1. If n is 1, you have 0 degrees of freedom for the interaction. You can't, n equals 1 for the block design. You can't get the interaction. So if n is greater than 1, in other words, the number of observations in each cell is greater than 1, then you can estimate the interaction. Okay? So I think we'll stop here, but we're going to come back and spend quite a bit of time on this section, and then the next section is just kind of an extension of this. And during the process of this, I'm going to give you a simple rule of computing expected mean squares, assuming that you have a balanced design. If you don't have a balanced design, for those of you that are taking, at some point we'll take stat 513 design, Jerry Hobbs used to always have people compute by hand expected mean squares, which can get complicated for unbalanced design. The way Ken Ryan is teaching it, he's actually using jump, which computes it for you. And that's good and bad. It's good because they can get hard to compute. On the other hand, it's maybe good to know how to compute it for some simple cases. Well, we're going to do some simple cases, but believe me, when you go from the balanced to the unbalanced case, suddenly doing it by hand is not so easy. We can do it simply for the balanced case, and that's what we'll do. And the reason is you'll find out with some sorts of designs, there is no correct error term. And you have to either make an approximation or do what are called synthetic f-tests. Because if you have certain random and fixed effects, you may not have a correct error term for certain treatments or interactions. So we'll get into that. We're not, as I said, we're going to have simple rules for computing expected mean squares. But if you don't know how to compute expected mean squares, you can have difficulty in determining what the correct error term is. Okay, any questions? Okay, well, I'm going to come back to this whole model matrix a little bit more, and then we're going to go into the two-way next time. Going from a one-way to a two-way is a much bigger jump than you might think.